In this video, I want to talk about the idea of sorted data. So here's a question for you. What exactly does it mean for something to be sorted anyways? So here I have basically on my slide, the sample array. It has a bunch of data in it, 1 through 9. It's sorted, right? I mean, you look at it, right, and you're like, oh, it's sorted, but what does that mean? What does it mean? Because we want, right, some sort of mathematical understanding of what it means to be a solution to our problem, right? Because we have some problem, right? So we have some problem, we have a problem P, right? And we have some solution S, right? How do I know that there is a match? How do I know that S really produces P, right? I need to know what my problem is so that I can build a solution for it, right? What does it mean to be sorted? So yeah, what does it mean? In this case, I have a nice little mathematical definition for you guys. So it says for all n, a of n less than a of n plus 1. So what is going on? A is, of course, the array, right? So A is this whole box over here, right? That is A. And then I have n. N is an index value, right? So this is index at 1, 2, 3, 4, 5, 6, 7. So let's say, hey, let's pick an n, right? So valid n, right? So n here, right, has to be basically between 0 and 7. So I can pick, n5, and what I get is, a sub 5. Let me try redrawing that. A sub 5 less than a sub 6, which ends up being 7 less than 8. It's obviously a true statement. As a true statement because this whole thing is sorted. So for any possible choice of n, right, from 0 to 7, I should put, this actually needs to be, this actually needs to be 6 over here. Because otherwise I'll have an equivalent of an index out of bounds there in my math proof. But yeah, so 7 less than 8. But yeah, it's a true statement, right? And this little kind of relationship here, right, is basically supposed to hold for every single one, right? So whatever is at index 0, right, is less than index 1. Whatever is at index 1 is less than index 2. Whatever is index 2 is less than index 3, right? And that carries through the entire thing. Basically, what we're saying is that every pair of elements is in order, right? The smaller one is before the larger one. And then by transitive property, that means that if each of the pairs, right, is in order, well then basically the whole thing is in order itself, right? That equality holds, right? So 1 is less than 2, 2 is less than 3, then therefore 1 is less than 3. It's going to mean basically everything is in order. So yeah, this is our definition here, right? So this is when we say that an array is sorted, this is what we mean, right? Is that this holds. For all n, a sub n is less than a sub n plus 1. And this value here, right, 7 and 8, right? These are keys. Here we just have a primitive data type, so it's not a big deal. But if we had a more complex type, we'd have some additional logic on there to pick out what is the thing we're comparing. All right, so question for you guys: is this all? Is this really over here a definition? Is that really complete, or do I need something else? So think about that for 1 second. So in this case, we're good, right? That's literally the only thing we need, right? We have a collection of elements. We're just saying for each of them, how are they related? Well, they're related by saying the smaller one is first, larger one is later. If it holds for everything in the collection, then it's good, right? It's sorted. So this is all we need. All right, so stepping forward, let's see. What does it mean for something to be not sorted? So here I have it, written on the slide. And this right now, all of a sudden, we've kind of broken up our array, right? Before it was perfectly sorted. Now we don't have that. Right now we've messed everything up. So how do we say that it's unsorted? Well, in this case, and actually, so depending on how long you took discrete math, you may remember how to do it. But basically, what we do is you want sort of like the negation of that. Before we were saying that this property holds for everything in that set or everything in that collection, array here for us. But now we're saying that there's some exception. So if I want to say that something's unordered, that means that there exists, right, some n, some index, such that the a of n plus 1 is less than a of n, right? So there's kind of this locally the order is off, right? So it's like over here, right? All of a sudden, these two elements over here, right, are out of order. Basically, that index 1, right, that value 1, right, is actually less than 3, right? Those are basically out of order, right? And we have actually a bunch of pairs here that are things that are out of order. And in fact, 1 is out of order with a ton of things. Actually, if I look, we can see that this is out of order as well. But as long as I have one particular pair of elements, right, that are flipped, right, that aren't in their proper order, what that implies is it's unordered. So I have at least one element that's out of order. It only takes one. All right, so I feel like I've accidentally put some art on the screen here. Like I can see there's like some eyes going on and a little mouth and stuff like that. I feel like I drew a little bug here. But anyways, that was not intentional. All right. Anyways, so the next thing to talk about is basically this idea of inversions. So inversions. So here, okay. So this we'll kind of keep as definition of unsorted. So the second bullet point, metric for a metric called inversions. So this is something, and we won't talk about it that much here. We'll have to come back to it later, but it'll be really valuable. But yeah, this is the definition given by the book. An inversion is a pair of entries that are out of order in an array. That's kind of the definition of saying that's what this is, right? This 3 and the 2, right? So 3 and 2, those two are, an inversion. All right, there's a problem there. All right. Quick micro example here, right? So we have this littler set because it's easier to analyze. So we have 3, 1, 8, 2. That one has 3 inversions, right? So 1 is out of order with 3. 1 is out of order with, well, it's in order with 8 and 2, okay. Let's see, 3 is out of order with 2. Okay, 3 is out of order with 1. Okay, then 8 is out of order with 2. And so, yeah. We get basically, these are our different little flips. So these basically are saying, all right, these are the reasons why our data isn't sorted, right? Each of these inversions. So you can notice basically that the biggest culprit here is probably number 3, because 3 is involved in 2 inversions, right? Each inversion is sort of this breakage of it is a break in it being sorted, right? And so if I have a particular element that has a ton of inversions, that means it's like way far away from where it's supposed to be. So these are the things we want to fix. Typically, as we go through sorting algorithms, they'll go and they'll fix. Well, the first one we'll talk about will basically fix one inversion at a time. So yeah, and this metric will kind of be important for us later, because what will happen is, so algorithms, right, do work on some data. They do some sort of manipulation of that data. The hope is, right, is we can have some algorithm that when it does that manipulation of the data, it fixes more inversions, basically as many inversions at a time as it possibly can. If you fix fewer inversions, you've done less work. You're still, really reasonably unsorted. If you manage to fix a whole bunch of inversions by doing one little thing, that's a good thing. And that we'll talk about kind of at the last third of the lecture is what we'll end up talking about that stuff in. All right. So yeah, let's hear the notions, right? So we have local changes, which are basically to say maybe I move an element one position over, which fixes one inversion, or I could have a global change. It's like where I take one element, I move it to the completely other different side of the array, in which case I'm going to basically fix all the inversions that are in between. So here, right, it's like if I move, let's see, I can't move 2 all the way forward, but if I move 3 kind of to the very end, I'll add one inversion and then fix 2. But point is, right, is if I move things a certain way, I hopefully can get this thing to be ordered faster than I would otherwise, right? If I can undo multiple inversions at the same time, I can maybe make progress towards being sorted a lot faster. All right, so hopefully this gives you guys some sort of idea, basically, of what it means to be sorted, right, in the mathematical terms, right? What does it mean to be sorted? What does it mean, to not be sorted? And also this idea of what an inversion is.